Many of you have probably seen the movie Interstellar, in which the protagonists aboard their spaceship have to explore a planet that is very close to the black hole Gargantua. So close that for every hour spent on the surface of the planet, on Earth, 7 years passes. Only a few hours pass for the astronauts who come down to the planet, while for their colleague Romilly, who remains aboard the spaceship, 23 years pass. But why does this happen? Well, to understand this, we have to take a step back to November of 1915, in which Albert Einstein, in 4 lectures at the Prussian Academy of Sciences, presented the theory of general relativity, the result of over 10 years of studies. In it, the scientist tried to connect his theory of special relativity with Newton's theory of universal gravitation. Very briefly, we remember that special relativity establishes that the laws of mechanics, electromagnetism, and optics are all the same in inertial reference systems, i.e., those in which a mass moves in uniform rectilinear motion, and that the light propagates in a vacuum at a constant speed, regardless of the state of motion of the source or of the observer. The equation underlying general relativity, also called Einstein's field equation, is based on the equivalence principle, which establishes that inertial mass and gravitational mass are equivalent. However, the respective definitions of those two types of masses are different. The inertial mass is proportional to the inertial of a body, which is the resistance to the change in the state of motion when a force is applied, while the gravitational mass is proportional to the interaction force of a body with gravitational force. The equivalence principle is so called because an observer jointed with the moving masses is unable to distinguish an acceleration due to an external force from that is produced by a gravitational field. The difference is visible only from a reference system that is not joined with the moving masses. To try to better understand this principle, Einstein himself proposed the elevator thought experiment. Let's imagine we're inside an elevator on the top floor of the Empire State Building and suppose there's no air in it. Suddenly, the carrying cable breaks and the cabin begins to fall freely with a constant acceleration equal to the acceleration of gravity, which for the Earth is 9.8 meters a second squared. A person inside drops a stone and a feather. The force of gravity attracts both of the two objects and the elevator in the same way, so the relative speed between the stone and the feather is 0. In other words, both the stone and the feather do not reach the bottom of the elevator, since the latter is falling with each of their own acceleration. The person inside a cabin would therefore rightly claim to be in an area of space far from the gravitational actions of stars and planets, since the two objects left to themselves remain suspended in midair. Let us now consider the opposite situation. The cabin is placed in an area of space where gravitational forces do not act, for example in a space shuttle in Earth's orbit. Let us also suppose that the elevator cabin is pulled upwards, away with the constant acceleration by means of a cable connected to the ceiling. If the person inside the elevator leaves the feather and the stone, they will stay in place since no force acts on them. However, the cabin floor is moving upwards, and sooner or later it will reach the two objects. The person inside the elevator, ignoring the external situation, may believe he is inside a gravitational field since, by letting go of the feather and the stone, they fall to the floor at the same time. The person himself also feels his own weight because of the floor pushing against his feet. It can therefore be stated that the effects of a constant acceleration on an observer are equivalent to those of a uniform gravitational field on the same observer supposed to be at rest. In this consists of the famous equivalence principle formulated by Einstein in 1911. Several experimental verifications of the equivalence principle has been carried out, and the main ones take into consideration two types of experiments, the gravitational balance and the gravitational redshift. The degree of precision with which the equivalence principle has been verified is so high that it is one of the pillars of all modern physics. Einstein, following these arguments, deduced that the field of equations of general relativity, which can be written in a very famous form that you may have seen on some slightly nerdy shirts. The Ricci curvature tensor minus 1/2 the scalar curvature times the metric tensor is equal to 8 pi times Newton's gravitational constant divided by the speed of light to the 4th power. All of this times the stress energy tensor. Are you lost? Don't worry. Let's try to explain its meaning. G mu v is the metric tensor, which mathematically expresses the properties of a curved spacetime. The indices mu and v represent the coordinates of spacetime and can assume different values. The spatial coordinates are usually indicated by the values 1, 2, and 3, while the time coordinate is indicated by the value 0. The metric tensor also allows to calculate the distance between points in a curved spacetime. R mu v and R take into account the curvature of spacetime. R mu v is the curvature tensor, and also in this case the indices mu and v represent the 3 spatial coordinates and the 4th time coordinate of spacetime. G is the universal gravitational constant, and c is the speed of light in a vacuum. T mu v is the impulse energy tensor, which represents the source of the gravitational interaction, which is not only the density of matter, but also its energy, and therefore also its state of motion. In practice, the mass that generates the gravitational field is contained in T mu v. Put simply, what do Einstein's field equations tell us? Well, they tell us that gravity is interpreted as a geometric effect, as the matter present in the universe determines the curvature of spacetime. Einstein's equations simply express the relationship between curvature on one hand and matter and energy on the other. The field equations also tell us that spacetime and time are not separated as in Newton's theory, but joined together in a 4-dimensional spacetime, 3 spatial and 1 temporal. Not only are space and time no longer absolute, but they're also intrinsically connected. Therefore, each point in spacetime, which defines an event, can only be defined through 3 spatial and 1 temporal coordinates. What makes this theory particularly difficult is a kind of feedback loop, that is to say, the curvature of spacetime is determined by the distribution of matter and energy distributed in the universe, which in turn is governed by the curvature of spacetime itself. Einstein's theory gives an interpretation of gravity, including Newton's theory, which remains valid as a particular case, where the masses that generate gravity, for example in the solar system, are not too large. The effect of any material body is to curve the space around it. This curvature causes the bodies to deviate from their rectilinear trajectory, thus causing what we call gravitational attraction. Another consideration: if a body is subject to acceleration due to gravity, it means it no longer moves with a uniform rectilinear motion, but with accelerated motion, and therefore Euclidean geometry. In short, the one that tells us that the sum of the angles of a triangle is 180 degrees. Again, for the equivalence principle, it is no longer valid in the presence of a gravitational field. In the presence of a gravitational field, spacetime is curved. This implies that, in addition to space, time is also distorted. That is, the closer we get to the source of a gravitational field, the slower time flows. And it is precisely for this reason that for interstellar astronauts who descend onto the planet in orbit around Gargantua, time flows much slower than it does for the colleague who awaits them aboard the spaceship. Precisely because the gravitational field generated by a hole is very intense, the black hole will produce a high curvature in the spacetime around it, and therefore the effect of time dilation will be more conspicuous. Would you like to travel close to a black hole like in Interstellar to experience this effect? Write it down in the comments below, but don't go too close to it because you're going to risk being inexorably swallowed up by its gigantic gravitational field. In the case of a planet like the Earth, its mass is much smaller than that of a black hole. Therefore, the curvature produced by our planet in spacetime is very small. It follows the same dilation of time will also be very small. So to observe it, we had to wait for the advent of atomic clocks, characterized by sensitivity of the order of a billionth of a second. In October of 1971, Joseph Hoefle and Richard Keating, to measure the relativistic dilation of time, boarded 2 separate airliners with previously synchronized cesium atomic clocks. The clocks made 2 turns around the Earth in opposite directions. Upon return, the measured times were compared with each other and with the time marked by a clock left on the ground. Compared to this, the clock that had traveled east was delayed by about 60 nanoseconds, while the clock that had traveled to the west had a 270 nanosecond lead. The detected time differences were in excellent agreement with the relativistic predictions, taking into account both the gravitational dilation of time due to the different altitude and the kinematic dilation of time due to the motion of the clocks. In the flight to the east, the speed of the plane is added to that of the rotation of the Earth, and the kinematic effect prevails over the gravitational one of the opposite sign. In 1976, the Italian physicists Luigi Briatore of the University of Turin and Sigfredo Lasciudia of the National Electrotechnical Institute, Galileo Ferris, today INRIM, National Institute of Meteorological Research directly verified gravitational expansion by comparing the times of two atomic clocks at rest, one located in Turin, height about 250 meters above sea level, and the other on Plateau Rosa, height of about 3,500 meters, which is differed by about 34 nanoseconds per day, in accordance within the experimental uncertainty within the theoretical prediction. In the pioneering experiments of the 1970s, the observed slowdown effects were on the order of 1 part in 10 to the 12th power, at the limit of the accuracy of the atomic clocks of the time, which were wrong by about 0.1 microseconds per day, or that's 1 second every 30,000 years. The most sophisticated clocks currently available, optical atomic clocks, have reached an accuracy of around 1 part in 10 to the 18th, which means they're wrong by 1 second every 10 billion years, roughly the age of the universe. These watches would allow you to observe the different passings of time even at low speeds and on gradients of just few tens of centimeters. Would you like to have such a precise watch, and what would you use it for? Write it down in the comments below. It should not be forgotten that the relativistic effects of time have also entered the daily life. GPS, the positioning system we use to locate a point on the Earth's surface with an error of about 10 meters, works by converting the travel times of radio signals exchanged between satellites in orbit at 20-kilometer altitudes and terrestrial receivers. Since the clocks on the satellites are in motion respected to those on the ground and feel a weaker gravitational field, the time they measure is different from the time measured by the receiver. There are two corrections, one of 7 microseconds per day due to the kinematic dilation of time. Satellite clocks go slower than that of terrestrial clocks, and another of greater magnitude and opposite sign of 45 microseconds per day due to the gravitational dilation of time. Satellite clocks go faster than terrestrial clocks. If these effects were not taken into account, the daily error on localization would be greater than 10 kilometers. The fact that the GPS leads correctly to the destination therefore represents a continuous verification of the theory of general relativity. The relativistic link between time and gravity has other interesting application implications. Ultra-precise clocks can act as highly sensitive gravity sensors, which can be used to measure the inhomogeneities of the Earth's crust, which determines small local variations of the gravitational field, or even to monitor the magnetic movements of volcanoes. These studies design a new field of research on which many meteorological institutes around the world are engaged.